Welcome. In this video I'll discuss firehose and mirror instabilities, and these are instabilities which arise when the pressure is anisotropic, and in the firehose instability is particularly at high beta, so it's quite relevant for things like solar and astrophysics, but less so for magnetic confinement devices. The mirror instability is a potential instability in magnetic mirrors, but it also occurs elsewhere wherever the perpendicular pressure is higher than the parallel pressure. So I'll introduce these in the context of CGL MHD. So this is an extension to MHD which includes perpendicular and parallel pressures. And then we'll discuss these two instabilities, the firehose and mirror, also known particularly in Russian literature as the centrifugal and diamagnetic instabilities. So the firehose is a kind of alphane wave which becomes unstable, and becomes unstable when the parallel pressure becomes too large. And the mirror instability is a kind of instability that occurs when the perpendicular is essentially the slow magnetosonic wave, so the perpendicular wave becomes unstable when the perpendicular pressure becomes too large. And so in the CGL MHD there are essentially equations for the density, velocity, the parallel and perpendicular pressures, and that for each species. So what's usually done is to assume a cold electron, cold electrons and hot ions, and then you can linearize these equations in the same way as we did for standard MHD, and you end up with a dispersion relation, which is this. So there's now a quadratic in omega squared, so you have a omega fourth term and omega squared term. There's still a quadratic, so it can be solved to find the roots and find when omega squared becomes negative, which is when you have instabilities. So here the usual, so V alphane, so V alphane squared. This is just b squared over mu naught rho. This is the alphane speed, or the square of the alphane speed. P perpendicular is the perpendicular pressure. Rho naught is the density. So rho naught is the density. So P perpendicular and P parallel are the different pressures. And then K perpendicular and K parallel are the wave vectors in the perpendicular and parallel to the magnetic field. Okay, so K parallel, for example, is just B dot K, and then K perpendicular is K minus K parallel. K parallel B, for example. Okay, so then we have equations involving perpendicular and parallel K vectors. So now we can look at the different components. So if you look at the parallel component first, so we look at cases where K perpendicular is much less than K parallel. So in this case the dispersion relation simplifies, so we just have omega squared. So this is now the alphane wave, or the shear alphane wave. So it's the parallel wave along the field lines, with if P perpendicular is equal to P parallel, so if these two are equal they cancel, and you just have the standard alphane wave. But you can see something strange happens here. If P parallel is large enough, then this whole thing can become negative, and at that point omega squared becomes negative. So if P parallel is basically bigger than the sum of the perpendicular pressures and this, so if P parallel is bigger than P perpendicular plus this B squared over mu naught, then omega squared can become negative, and so omega becomes imaginary and we have an instability. So because B squared over 2 mu naught is the magnetic pressure, we can write this also in terms of betas. So we can define the parallel beta as the ratio of the parallel pressure to the magnetic pressure. So it's divided by B squared over 2 mu naught is the magnetic pressure, and the same for the perpendicular pressure. So B perpendicular is just the perpendicular pressure divided by magnetic pressure. And in that way we can define the instability occurs when beta parallel is bigger than beta perpendicular plus 2, because you here have a factor of 2 in there. And so the firehose instability occurs when beta parallel must be bigger than 2. So that's the minimum if beta perpendicular goes to 0. And beta perpendicular can't be negative, so this is kind of a minimum beta that it must occur at, and therefore this is only really relevant for space plasmas, so space and astrophysics, because in a magnetically confined fusion device like a tokamak or a mirror, beta is much less than 1, and so the firehose can't occur. So what's the mechanism for this firehose instability? Well, it may help that one of the other names for it is the centrifugal instability. And essentially, if you imagine a field line with an alpha wave on it, so we have a field line which has some kind of wave traveling along it. This is B, and now we have a particle which is traveling along the field line, but has a very large. So it's kind of winding around here, so it has a very large parallel velocity. So V parallel is much bigger than V perpendicular. So we've got some charged particle here. And what it experiences, because it's being curved, has a centrifugal force. So essentially there's a radius of curvature here. So there's some kind of kappa vector. So there's kappa, it's like 1 over this radius of curvature here, and so there's a centrifugal force which the particle experiences outwards from this curve, and this force, if you put a force on charged particle in the magnetic field, you end up with a drift, and so there's a centrifugal drift perpendicular to both the field line and the force, and so it's out of the page here, and these drifts, if they're large enough, can lead to enhancing this perturbation. So there's a restoring force, which is due either to the magnetic tension. So if you have a strong magnetic field, you end up with a restoring force due to the currents you induce, produces a force which acts to straighten the field lines. And so a high magnetic field will stabilize this mode, and it's also stabilized by the plasma pressure. If you're perturbing the field like this, you're changing the pressure of the plasma, and so if you have high perpendicular pressure, that also acts to push the field lines back to where they were. And so if you have either a low beta, so high magnetic field, or high perpendicular pressure, then these are stabilized. So let's write that down here. So these are stabilized by magnetic field tension or perpendicular pressure. Okay, so the other kind of instability we want to look at is the mirror instability. And this occurs in the opposite case, where we have a very high perpendicular pressure, and is more relevant for magnetic confinement devices, particularly mirrors, hence the name. So this is a kind of slow wave, so it's a perpendicular wave, which becomes unstable in some circumstances. So it has the K perpendicular is much bigger than K parallel, and we solve it by using this expression we had up here. So we take this full dispersion relation, so it's a quadratic in omega squared, and then we label these things here. So this for example, we're going to label A2 is a coefficient, so this coefficient in front of the omega squared. I'm going to label all of this whole thing as A0, because there's no omega squared for power in front. So we just have omega to the 4 minus A2 times omega squared plus A0 is equal to 0. Allows us to get rid of most of this, well, hide most of these details. So we have, of course, it's just a quadratic, so we can just write down the solution. So in terms of omega squared, so we have the standard quadratic formula. There's a few things to note here. That first, A2 must be positive. Have a look here. So each of these terms in here, every term is positive. So we have K squareds, alpha in speed, squareds, pressures, all of these are positive. So A2 is bigger than 0. You can also show, although the derivation is a bit longer, that this part here is also always bigger than 0. So we have A2 is bigger than 0. So this part here is always larger than 0. And remember that if omega squared is positive, then we have a wave. If omega squared is negative, then we have an instability. And so we're looking for cases where omega squared is negative. And so we have an unstable branch when this part here becomes larger than this part. So when the square root of A2 squared minus 4A0 becomes bigger than A2. So if this part is bigger than that, then we have an instability. Because we'll have two branches, a positive and a negative branch, and the negative branch will be unstable. We'll have omega squared less than 0. And this of course occurs when A0 here is less than 0, then this will become larger, and so therefore when A0 is less than 0, it's unstable. If you write out what this means, so write out this here. So this is A0 written out in a slightly different way in terms of the parallel beta pressure, and A, which is an anisotropy. So A is the anisotropy in the pressure, which is because everything cancels out, ends up being the anisotropy in the temperature. So if this is 1, then you've got isotropic plasma. And so you have these two conditions on things like the perpendicular and the parallel wave vectors. So if we look at the case where K parallel dominates, essentially you want this part here to be less than 0. And so you can see the part that makes it less than 0 is this bit here. And so we have if the factor A becomes too large, then this whole section here will become negative, and then we'll have an instability. So we have rearranged this a little bit. So in terms of the perpendicular and parallel betas, this gives this relationship. This is the condition in the CTL theory for the mirror instability. Now there is a factor out here, so this factor of 6. This, if you do the full kinetic calculation, this becomes 1 in the kinetic theory. So the mirror instability occurs at a much lower anisotropy and in kinetic theory than it does in CTL theory. Okay, so the mechanism for this, it has a more descriptive name, is the diamagnetic instability. So the basic mechanism is that perpendicular pressure, because corresponds to ions moving around on their field lines. So if you have a field line like this, and you have a particle with a high perpendicular velocity, so it has a v perpendicular like this, that is a current loop which makes a magnetic field which opposes the original. So you have a B field here, you have a particle moving around in orbit. This makes a magnetic field which is in the opposite direction, so it opposes the original magnetic field, and hence the magnetic field strength drops. So if you have a very high perpendicular pressure, you reduce the magnetic field strength, and if you reduce the magnetic field, you produce a potential well that particles can get trapped in, and so you increase the density and you potentially increase the perpendicular pressure. And so there's a runaway instability where you have high density regions producing a high perpendicular pressure, and that reduces the magnetic field and leads to more trapping, and so you end up with a magnetic fields which may start. So if I try and draw, let's see here, so a bunch of magnetic fields which basically end up being deviating like this. A bit exaggerated like this. So these are our field lines, these are B field lines like this. What we end up with is regions where the field lines are grouped together, so high B field, and regions with low B field. And the particles flow from these high field regions into low field regions. This, so we have a K perpendicular, which is this way, so we have a slow wave across the field lines, and they have a very elongated structures along the field lines. So it flows along the field lines like this into high density regions. So delta N increases in these regions here. So delta N increases. High perpendicular pressure reduces the magnetic field strength, and so you get in these high density regions the field drops, and it makes these perturbations even larger. I was written this down here. So perpendicular pressure reduces magnetic field strength, and this creates potential wells which more particles can fall into and create a higher density and reduce the field even more. And so there's a runaway process there which creates an instability. And so the signature for this is that you have high density regions and low magnetic field regions. So the density perturbations and magnetic field regions perturbations are anti-correlated. So meaning that the high density regions have low magnetic fields and low density regions have high magnetic field. Now these are called mirror instabilities because one of the main places they can occur is in magnetic mirrors. So magnetic mirrors work by having essentially a high field at the end and low fields in the middle. So this is again magnetic field or field lines. So I'll cover them in a bit more detail in earlier lectures, but essentially you have a throat where you have a high field. So this might be the coils around here, and you have a low magnetic field in the middle, and this means you have a field lines essentially going through the middle of the machine. And so high K parallel, high V parallel essentially are lost, and what you end up with is any particles which have a high perpendicular velocity are trapped. So your high perpendicular velocity particles, these are reflected, and so these essentially bounce back. And so what you end up with in velocity space, if you plot like if this is like V perpendicular, this is V parallel, for example, what you end up with are lost cones. So you end up with any particles which have too high parallel velocity are lost. So all these particles in here are lost. So these are lost. And the particles that are trapped are here have high perpendicular velocity. And so therefore what you end up doing is dropping the parallel velocity, parallel pressure, because you're losing these particles, and increasing the perpendicular pressure. And so therefore the lost cone produces P perpendicular much bigger than P parallel. And in this case you can get these mirror instabilities or diamagnetic instabilities. And what the instabilities do is they grow and they scatter particles from perpendicular into the parallel. And so the instabilities when they grow, they will reduce the anisotropy, and so these instabilities tend to scatter particles into this lost cone. And so these mirror instabilities enhance the loss of particles from the ends because they scatter perpendicular trapped particles into lost particles. And these are one of the reasons why magnetic mirrors are no longer studied for magnetic confinement fusion, is that the scattering into the lost cone is typically even worse than you'd expect from collisional scattering.